Let's look at the following three examples using Green's theorem. Number one, evaluate the line integral of xy to the fourth dx plus x squared dy, where C is the rectangle with vertices 0, 0, 2, 0, 2, 1, and 0, 1. Well, I should have said C is the boundary of that rectangle. Anyway, to do number one, let's look again at Green's theorem. Green's theorem states, let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by the curve C if P and Q have continuous partial derivatives on an open region that contains D. Then the line integral P dx plus Q dy over the curve C is equal to this double integral over the region D of the difference of these partial derivatives with respect to the area of that region. Okay, I will explain pieces of this as we go along in each of these examples. Let's go back to number one. We'll begin this one with a sketch of the region. So we have vertices at 0, 0, 2, 0, 2, 1, and 0, 1. So the curve C is actually this path around this rectangle. So we're looking at an integral around the curve C, along the curve C of x y to the fourth dx plus x squared dy. And so in this example, the function p is this x y to the fourth, q is this function x squared, and we're going to need to know the derivative of q with respect to x, so that's 2x, and we'll need the partial of p with respect to y, so that's 4x y cubed. So, does Green's theorem apply? Yes, C is a closed curve. It begins and ends at the same point. It is piecewise smooth, so it has tangents on intervals only, save for a few instantaneous points. What else do we need? It's a simple curve, so it doesn't cross over itself. And D is the region that's bounded by that curve on which these derivatives are all continuous. So Green's theorem applies. Let's use that to see if that comes up with a quick, easy answer for this line integral. So that's the region D. And I have to do the derivative of q with respect to x minus the derivative of p with respect to y. And that's still with respect to the area. So I'm going to make a choice now as to how to integrate over this region. And because it's a rectangle, rectangular coordinates will work perfect. So let's go from x equals 0 to x equals 2 on the x-axis. And then from y equals 0 to y equals 1, this was the point 1. So we'll have this integrand 2x minus 4xy to the fourth. I got y on the inside, so I got to do dy, and then I have dx on the outside. So integrating with respect to y first, I'm going to get 2xy minus, integrating this with respect to y. Yep, I knew I had a mistake there somewhere, and now I've spotted it. I had 4xy cubed for this differential of p with respect to y. That should have been a 3 right there. Copying that 3. So that's the dq dx minus the dp dy right there. Right there. Okay, so moving on. So integrating with respect to y, I got 2xy minus integrating this with respect to y. That'll become a 4. I divide by 4, so this is actually xy to the fourth. and I'm plugging in y equals 0, and I will plug in y equal 1, and then I'll finish with differentiating with, or integrating with respect to x. So plugging in y equal 1, you get x equals 0 to x equal 2, 2x minus x. When you plug in 0 for y, both of these terms are 0, so that all disappears. So this is 0 to 2 of just the function x with respect to x. So x squared over 2, evaluated at 0 and 2. So that's 4 over 2, and we have an answer of 2. Okay, that takes care of the first one. Let's move on to the second one. Number 2 says, evaluate the line integral y cubed dx minus x cubed dy, where c is the boundary of the region between two circles centered at the origin with radius 4 and radius 5. So Green's theorem requires a positively oriented, piecewise smooth, simple closed curve in the plane, and D to be some region that is bounded by C. And P and Q have continuous partial derivatives on that open region that contains the region D. Then we can apply this equality. So to be simply connected would mean some region like this one or this one. These regions are not simply connected. And so this having a hole here in the region means that it's not simply connected. And in this particular example, we've got a circle with radius 4, a circle with radius 5, and we're looking at evaluating a line integral on a curve that is bounds the region between these. So really the region D that I'm interested in is all of this region between the curves. So the region is that area there in yellow. The curve C is actually the boundary of that region. So we're definitely looking at one of these not simply connected region. However, we can handle that still because of the type of region that it is. It has just this one hole in it, so it's easy to handle in the following way. Green's theorem can be extended to apply to regions with holes, that is, regions that are not simply connected. Observe that the boundary C of some region D shown in figure 9 here consists of two simple closed curves, C1 and C2. We assume that these boundary curves are oriented so that the region D is always on the left as the curve C is traversed. So this is the positive orientation, so that the region is always to the left as you traverse the curve. So the positive direction is counterclockwise for the outer curve C1, but actually clockwise for the inner curve C2. So for a region that's got a hole in it, we divide that region. If we divide that region D into two regions, D prime and D double prime, by means of the lines shown here in this figure, and then apply Green's theorem to each of the regions D1 and D prime and D double prime, then we get the following. Double integral over the entire region D can be made up of this simple closed region over D prime plus this area of this simple closed region D double prime. We're just adding all the area for D prime plus all the area for D double prime. And in each of these cases, Green's theorem would apply, and we get each of these two line integrals. But the beautiful thing is that each of these parts, these sort of bridges here, these blue segments, we traverse them in opposite directions, and so the calculation of the line integral over those intervals will cancel. Since the line integrals among the common boundary lines are in opposite directions, they cancel. So here we are just making the statement that the double integral over that region D with respect to the area is just the resulting line integrals with the common boundary parts of the line integral already canceled out. And so this is the total line integral over the entire curve C that's made up of these two independent separate curves C1 and C2. And so that's how we can apply Green's theorem to some region D where it has a hole in it. So we're looking at a line integral on some curve C that is the boundary of this region here between these two circles of y cubed dx minus x cubed dy. But we're going to make two simple closed curves out of these two curves by taking like this curve and then separately this curve with these orientations. And so beautifully, if we want to do this on this entire curve C that's actually made up of C1 and C2 and these little bridges in between, beautifully they just cancel out because they are each of them traversed in opposite directions. The red curve going this way, the black curve going that way, here the red curve going this way, the black curve going that way. So let's just say that we could break it up into those two and recognize that we'd be canceling out whatever you might call those little connectors. They cancel out in the final calculation because they are the same function traversed in opposite directions on the same curve, on the same segment of curve. So they would cancel out. And so it's right here that Green's theorem says, well, since this region is bounded by those two curves, we can just integrate over the region with this differential in Q with respect to X minus the differential in P with respect to Y with respect to the area of the region that is bounded by those curves. Now this region is circular, so it'd be much easier to integrate with respect to convert to polar coordinates. Now, I also need to figure out what is the dq dx and the dp dy, so maybe I'll just get that taken care of right at this moment. So what's the partial of q with respect to x? So q is this guy, so that's negative, that's the p, that's q. So this is negative 3x squared. Partial of p with respect to y, well, that would be 3y squared. And so now my double integral over the region R of the partial of q with respect to x minus the partial of p with respect to y integrated with respect to the area would be over that region, we'll say from theta equals 0 to theta equal 2 pi to represent the angular rotation around the circle, minus 3x squared minus 3y squared. And now forgot Green's theorem. I need a double integral here. So I need to go from r equals the inner radius. The inner radius was 4 to the outer radius 5. Then I have negative 3x squared minus 3y squared. Now in polar, I've got r dr d theta as the differential in A. All of this together is dA. That's the conversion into polar coordinates that requires that. So let's factor out the negative 3. It's constant in all the integration. And if I factored out the negative 3, I've got x squared plus y squared, and actually that x squared plus y squared is equal to r squared in the conversion to polar coordinates. So now we have negative 3 r cubed dr d theta, and the rest of this is pretty easy now. And so there ends example 2. Okay, so finally for the last example for this video, let's go to number 3. Find the area between the parametric curves x equal t minus t squared and y equal t minus t to the fourth on the interval t equals 0 to t equal 1 using Green's theorem. So what's really neat with Green's theorem is that this is one way in which you might find area if you run this equality backwards. If you start on the right hand side, set up a double integral, then you can convert it to a single line integral if that's easier. Depends on the way in which the question is stated and depends on the boundaries and the information that's given. It might be actually convenient to go the reverse direction. Of course, we have to confirm that Green's theorem actually applies. Let's take a look at this graph of these parametric curves. Well, it's kind of hard to tell from just what's given what exactly it looks like. I mean, I do know that if you plugged in 0, you get 0, and actually if you plug in 1, you get 0. So I know these both of them begin and end at the origin, but that doesn't mean it's a simple closed curve. Let's take a look in Desmos. All right, so yep. That's the curve that's generated by those parametric equations. It looks like it's defaulting 0 to 1. So if you go outside of that, you don't have something that applies that Green's theorem applies. But on that interval, it looks right. So if C is positively oriented, actually, I need to confirm that actually the orientation is increasing out to this point and then coming back to 0, 0, so that the region is this part of the graph that's between these curves, and then it's positively oriented, right? So after confirming that, then we can proceed with Green's theorem. So the principle that we use here is this fact that another application of the reverse direction of Green's theorem is in computing areas. Since the area of D is this double integral over the region D of this factor 1 with respect to the area, we can choose functions p and q so that that difference of partials in the integrand of Green's theorem is equal to 1. So we can go with this choice, p is 0, q is x, or we can go with p is minus y and the q is 0, or we could both have p minus 1/2 y, q 1/2 x. There may be some cases where it might be easier and faster to go with either of these two. In this example, I'm going to choose this option. And you can see that the derivative of q with respect to x, this would be 1/2, and the derivative of p with respect to y, that's negative 1/2, and so you do 1/2 minus negative 1/2, and you get equal to 1, so that works. And so we could choose either one of these three different options, and I'm using this last one. Okay, so I have x given here and the y given here, and I'm going to use this form. So the area is 1/2 this integral where Green's theorem applies on this curve C that's determined by these curves. X differential in y plus, minus y differential in x. Now, the way I'll sort through this is this line integral I can put back as an integral of some vector valued function dot some differential in r, which here I'm going to say some vector value function, and this differential in r, what I could do is I'll write that as dot r prime t and the differential in t. That way I can use the parameter, whatever parameter happens to be given here, rather than differentials in the or the increment of the position along the curve. This is just with respect to the change in the parameter. So I'm writing it this way so that I can remind myself that what I want to do is figure out what is the vector value function f. This is actually the p, this is actually the q, so the vector value function that I'm using is minus yx. So that's f. R is actually a vector value function that will trace out the curve. So that's the x, y values along the curve, which are these components that I have up here. And so I'm also going to need r prime. So that's 1 minus 2t and 1 minus 4t cubed. So the area, 1/2 of this integral where Green's theorem applies for this dot product of f, and the you could say velocity function or the rate of change of the position with respect to t, and then integrated with respect to t. Actually, now that I've got that dt on there, I could use the bounds for this curve, which are 0 to 1 in the parameter. Now I'm going to put everything in terms of t, so if I have minus y, so I'm copying down minus y, so that's minus t to the 4th, and then the x, which is given by this t minus t squared, dot with the derivative of these, so that's the derivative of the x and the derivative of the y. Alright, so now we can do the dot product. Well, maybe one more step just to avoid a mistake. I just wanted to distribute that negative in that first term there, and the rest of this I'll just copy out. And now I'll actually do the dot product. Okay, so there's the dot product. Now we FOIL out. Here I'm just distributing the first term, the outside, inside, and the last. Again, the outside, or first, and then the outside, then the inside, and then the last. We've got some like terms here. We can combine the t to the 5th term. That cancels. I mean, those combine. And the t to the 4th term. There's a t squared term we can combine. And the t's cancel. And from there, it's pretty straightforward. Okay, there it is. That's the answer for the third one. Okay, and that's the end of the video. I hope it's been useful and helpful and maybe even interesting. Okay.